Welcome back, everyone. This is Professor Herring. In this video, we're going to start Chapter 15. We're going to look at chemical reactions and what causes them. So let's begin. First thing that we need to understand is that during any chemical reaction, we're converting between elements or molecules that are what are called reactants, and they form what are called products. But that mass is conserved. We're not changing the identity of the element, but changing rather the identity of the molecule. And this is where we get the idea of what's called a balanced chemical equation. And so what's really going on is that we're changing the bonding patterns, we're changing where the lone pair electrons are throughout the elements and molecules, but that there's no matter that's created or lost. The mass of the reactants must be equal to the mass of the products. And therefore, the number of each element must be equal in both the reactants and the products. So, for example, if we look at the complete combustion of ethane, we're changing forms. It's going from the form of ethane to carbon dioxide and oxygen to carbon dioxide and water. However, there's still the same number of each element. So the coefficient determines the number of molecules, and the subscript helps us to determine the molecular identity. And so if you were to look at the space filling, or the ball and stick models here, we see we could have two ethanes with 7 oxygen molecules, and they get rearranged. What was bound to what is changed, but we have the same number of each element that we started with. So we had 4 carbons, we have 4 carbons. We have 14 oxygens and 14 oxygens. And there's 12 hydrogens and 12 hydrogens. Just where they are in relation to each other has now changed. And you want to be able to recognize the patterns of reactivity rather than memorizing specific interactions or reactions. There are literally millions and millions of reactions that could occur, but we can categorize them into a handful of different types of reactions. And so you want to be able to recognize what type of reaction we can classify it as that will help you to understand what's going on and to predict what to do with it. One such category are combustion reactions. We saw one already with ethane, but in this case we're looking at propane combusting with oxygen. Generally speaking, combustion reactions involve some kind of organic molecule always reacting with oxygen. And it generally produces carbon dioxide and water. Cases where that might vary are if we have an organic with nitrogen in it or sulfur in it. And those are going to affect, we will get different products in the end if we have sulfur or nitrogen rather than just hydrogen and carbon. So you might get some things like sulfur dioxide or nitrogen monoxide or nitrogen dinitrogen monoxide or nitrogen dioxide, a variety of different compounds there. But we're going to focus mostly on organic plus oxygen yields carbon dioxide and water. Another category is what are called combination reactions. And these are cases where you take 2 elements or compounds and they form a single compound. They're fairly simple. All you need to do is recognize that we have multiple different things becoming one particular type of thing. The coefficient here does not matter as much as the identity. In other words, just because we made 2 magnesium oxides doesn't mean this is not a combination. But if we had made magnesium oxide plus something else, then it would not be combination. The reverse of combination is a decomposition reaction. And that's where you take one particular type of molecule and it breaks down into smaller molecules or elements. And you can see that this is the opposite of combination. If we were to reverse these processes, then we would get the reverse process. So the reverse of combination is our decomposition. So let's now try a problem. What's the coefficient in front of water in the balanced reaction for the combustion of ethanol? First thing you want to do is write out the unbalanced molecular formula. That's going to be ethanol plus oxygen, and because it's an organic, we're going to yield CO2, carbon dioxide, and water. First thing I would recommend doing here is balancing the carbon first, or really the hydrogen. It doesn't matter in this case. But you should definitely not balance with respect to oxygen. And the reason for that is because oxygen shows up in two different molecules on both sides of the equation. And so trying to get it to balance properly would be a nightmare. Instead, you want to pick something pick one element that is in one reactant and one product. And of course, it has to be in both a reactant and a product, but you only want it to be within one reactant and also one product. So if we look at carbon, we see that we have two carbons on the left and only one on the right. So to balance that, we need a coefficient of 2. Now we can balance the hydrogen. We have 1, 2, 3, 4, 5, 6 hydrogens on the left and only 2 on the right. So then we need a coefficient of 3. For oxygen, we now have, if we can do a note keeping here, we have 4 oxygens plus 3 oxygens, and we only have 2 on the left, which means that we need 5 more, or in other words, we need no, excuse me, I've missed, this is why you always double check. I've missed this oxygen here, so we've got 3 oxygens on the left, 7 on the right. Let's double check that. 1, 2, 3, 4, 5, 6, 7. We have got 1, 2, 3 oxygens on the left. So we need to change the coefficient in front of the oxygen molecule to be 3. So now we can double check. Look at the carbon, hydrogen, and oxygen on both sides. We've got 1, 2 carbon, 1, 2 carbon. Hydrogen has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And oxygen is 1 plus 6 is 7. And then 1, 2, 3, 4, 5, 6, 7. 7. So now we know that we're balanced, which means then that the coefficient in front of the water is going to be 3. Always double check your answer. Make sure that the numbers on both sides add up in the equation. Within aqueous solutions, or solutions that are water-based, we have different types of reactions that can occur. One category is called single displacement reactions. An example of this would be zinc metal reacting with aqueous copper sulfate to produce zinc sulfate and solid copper. We also have double displacement reactions. To understand where these terms come from, think of this like you've got a pair. You have A and then B attached to C, and now you have A attached to C plus B. This is kind of like you have two people going out on a date. Random person with a hat comes along. We got a girl and a boy. And the random person comes, breaks them apart. He runs off with the girl and the boy. is left crying. That's a single displacement. A double displacement reaction, it's also known as a metathesis or an exchange reaction, is where we have two sets of partners that swap. And so these have driving forces that we either label as precipitate formation. And again, we have something like A, B, and C, D. And now the A and the D are combined and the B and the C are combined. Weak or non-electrolyte formation. Sodium hydroxide with hydrochloric acid will form salt and water, which is a non-electrolyte. And then gas formation. Gases are also non-electrolytes. And something to notice here is that in all cases, our product is essentially going to be inert. This formation of this inert product is what drives the reaction forward. And the reaction up above, this is what we call a redox reaction. And these are four very common driving forces that make the chemistry occur. And in fact, if we were to look at the other reactions we saw, the combustion, combination, decomposition, those all tend to fall in the category of redox reactions. So it turns out that the majority of chemical reactions are redox reactions. Let's take a closer look now at precipitation type reactions. We use what are called the solubility guidelines to determine whether or not a precipitate is going to form. These are on the data sheet, and so I recommend that you become familiar with interpreting the data sheet so that way you can use it on the celebrations of knowledge. And so it's divided up into two categories. One where the rule is that things are soluble, and then another where it's showing things that are not soluble. And so when you take a look at the first rule, it lists that ammonium plus all of your alkali metals are soluble, and that there's no exceptions to this rule. Then when you take a look at some of the larger polyatomic ions, nitrates, perchlorates, acetates, those are all soluble with no exceptions. Finally, you have some smaller monoatomic ions, the halogens, the halides, chloride, bromide, and iodide. And those are soluble with only a few exceptions. And then you finally have some other larger molecules with larger charges that are generally soluble, but those tend to have more exceptions. And notice that in those cases, most of those exceptions are with highly charged cations. There's other rules as well dealing with phosphates and hydroxides and whatnot, but we're going to focus on, well, we'll get to those here in just a moment. In the cases for insoluble salts, we have carbonates and phosphates, and those are going to be insoluble or form precipitates with the exception of this first group, which makes sense. We said that there's no exceptions to these. And so these essentially are always insoluble unless they're bound with the things that always have to be soluble. And then we have hydroxides and sulfides. And those are generally insoluble with the exception of the alkali metals and some of the alkaline earth metals. And so again, what soluble means is that it's going to be aqueous in the end. Insoluble means that it's going to form a precipitate in the end. So let's try a problem. Which solution would form a precipitate when mixed with bismuth tribromide? Well, we've got a variety of different compounds here. So bismuth and bromide. There's a couple ways you can approach this. Evaluate. Let's just look at bromide in each case. Bismuth, if you look, it doesn't show up anywhere. And so let's take a look and see things for bromide. Bromide is almost always soluble with a few exceptions, and that's mercury, silver, and lead. And so bromide, we're going to have a precipitate. So if we mix barium with bromide, that's going to be aqueous. Okay? Lithium with bromide, that's going to be aqueous. And then lead with bromide, that's going to be solid. So we're going to get a precipitate there. But that's not all. We need to consider what's the effect of the bismuth. Well, so let's take a look. Hydroxides are generally insoluble, except with alkali metals, ammonium, and some of the alkaline earth metals. Since bismuth is not in that category, bismuth hydroxide is going to be a solid. And then when we look here, if we look at bismuth perchlorate, we see that perchlorates are always soluble, no exceptions. So this is going to be soluble, aqueous. And so we form precipitates for both A and C. Again, there we have bismuth hydroxide and lead bromide. Now, what if we wanted to, how would we represent those types of reactions? We use what's called net ionic or molecular full ionic and net ionic equations. And the net ionic equation is the kind that only shows the chemicals that are directly involved in the reaction. Or in other words, this tells us about our driving force. So, first thing that we want to do, let's say that we've got the following molecular equation. And initially, all we know is that we have lead nitrate reacting with potassium iodide. If you could be told that these two things react and you want to determine what's the net ionic equation. The first thing you need to do is write out a balanced chemical equation. And you want to start by making sure that the charges match up. In other words, we know that you have to know nitrate's a -1 charge. And therefore, lead has to be a +2 charge. Iodide is always -1, potassium is always +1. So when they combine, you're going to need 2 iodides for lead and 1 nitrate for 1 potassium. A very common mistake would be to use the wrong ratios. And so a little trick, if you will, is to take the substance that you're combining and the charge becomes the subscript. So PB1, I2. It's simplified into PbI2. Okay? So you want to make the charges match up, and then, only then, do you deal with coefficients. If you start to deal with the coefficients before your charges are matched up, you're going to make mistakes. Then you want to dissociate strong soluble electrolytes to write out the complete ionic equation. So we know that they're strong electrolytes when they are listed as aqueous. Okay? We're going to keep together anything that forms a solid, liquid, or gas. Common mistakes here would be to we need to convert the coefficients on polyatomic ions into we need to convert the subscripts into coefficients. Make sure that you include the charges and the states of matter. And then identify the spectator ions. Those are ions that show up on both sides of the equation. In this case, that's going to be nitrate and potassium. And then what's left over is going to be the net ionic equation. And this should be balanced already if you balance it properly at the molecular equation. Let's try a problem. What's the net ionic reaction when silver nitrate reacts with sodium chloride in aqueous solution? So first thing we want to do is write out the balanced molecular equation. That's silver nitrate reacting with sodium chloride, and we're going to swap partners. Our silver is going to react, or it's going to combine with the chloride, and the nitrate with the sodium. That gives us silver nitrate and silver chloride and sodium nitrate. In order to determine the states of matter, you need to look at the solubility rules. And the solubility rules indicate that chlorides are soluble except with silver, mercury, or lead, which means that it's solid. And nitrates and sodium ions are always soluble. Write out the complete or the full ionic equation, dissociating each of the aqueous substances into their ions. And notice that we keep together the polyatomic ions. So let's finish this up here. Molecular ions or other molecules stay together. So you need to know your polyatomic ions. You need to recognize when things are molecular, when they have covalent bonds. So that would be, for example, I2, H2, F2, C6, H12, O6. All of these are covalently bound only, and so they will dissolve, but they will not dissociate. Then we eliminate our spectator ions and rewrite with the net ionic equation. Let's talk about two other kinds of reactions that fall in this category of double displacement. One is an acid neutral. It's called an acid-base or neutralization reaction. This is where we take an acid and a base, react it to form what's called a salt and water. And a salt is, in these cases, we're going to see salts are just combinations of metals with nonmetals. And in this case, the formation of a weak or non-electrolyte is the driving force. So let's take a look at an example. In this equation, we're going to have hydrochloric acid with sodium hydroxide. That forms sodium chloride and water. Water is always going to be liquid when we're doing neutralization. Generally speaking, these will be aqueous, but you should always double check with the solubility rules. Then we dissociate soluble strong electrolytes. We know that strong acids and strong bases, by virtue of the label strong, will dissociate fully. Salts also dissociate when they're aqueous, and then water stays together. Identify the spectator ions and eliminate them. And that's going to produce our net ionic equation of hydrogen ion plus hydroxide yields water. This is the net ionic equation for all strong acid-base neutralizations. We're going to look at a moment at what it looks like for weak acids and bases. Let's do that now. So if we have a weak acid and base, let's take hydrofluoric acid. We see that we still get the double displacement. However, when we dissociate the strong electrolytes, we keep together hydrofluoric acid. This means that you need to know what the strong acids and bases are. Hydrofluoric acid stays together. It does not dissociate appreciably in water, and so we keep it together. Sodium hydroxide is a strong electrolyte, so it dissociates, and that's going to yield sodium fluoride ions, which are dissociated, and water. And that means for our full ionic equation, we have the hydrofluoric acid that's together. If this were a weak base, then it would be the weak base that's not dissociated. And so our spectator ions in this case are only the sodium ions, which when we eliminate gives us a different net ionic equation than in the case of a weak or a strong acid and a strong base. the final one we want to talk about is gas formation. So this could be in the case of where gas is formed directly, case of carbon dioxide, hydrogen sulfide, nitrogen, sulfur dioxide, or as the product of decomposition. So that happens if we have carbonic acid that's formed in water that decomposes into carbon dioxide and water. So here's an example of baking soda and vinegar. In this case, we have sodium carbonate with acetic acid. Both of these are, in fact, weak acid and weak base. That's going to form carbonic acid and sodium acetate. The carbonic acid is going to break down into carbon dioxide and water. And we can see that if we just redistribute one of the oxygens. So our new molecular equation is as follows. And so when we dissociate, remember, we can only dissociate strong electrolytes. Acetic acid is a weak acid, so it's a weak electrolyte. Salts are strong electrolytes. And so we get dissociation of the sodium ion from the bicarbonate. No dissociation shown for the acetic acid. Carbon dioxide and water remain as molecules, and then full dissociation of our ionic salt. We eliminate the sodium ion, which gives us a net ionic equation as follows. So that's it for this video. Thanks for watching. If you have questions, you can ask on Piazza and office hours or recitation. See you later.